Imagine waking up one morning to discover that the sun has disappeared, not from the sky, but from the ocean. Not the deep ocean, where darkness has reigned for billions of years, but from the surface waters where light has always danced through the waves, where photosynthesis has powered the greatest abundance of life on Earth. This is not a distant hypothetical scenario confined to science fiction, but a plausible consequence of planetary catastrophe. A massive volcanic eruption series, an asteroid impact, or runaway atmospheric changes could shroud our world in perpetual twilight and eventually, absolute darkness. The oceans, which cover 71% of our planet's surface, would transform into something unrecognizable. Within months, the familiar blue-green waters teeming with phytoplankton would fade to black. Within years, entire ecosystems built on sunlight would collapse. What happens next is a story written in the language of evolution, desperation, and the stubborn refusal of life to surrender. The first casualties are almost invisible to us, yet they form the foundation of everything. Phytoplankton, those microscopic photosynthetic organisms drifting in the upper ocean layers, are the primary producers that feed nearly every marine food web. When the light fails, they die within weeks, their populations crashing by 99% or more. The zooplankton that feed on them follow soon after, creating a cascade of starvation that ripples upward through every trophic level. Fish that have evolved over millions of years to hunt by sight suddenly find themselves in an alien world where their most refined sense has become useless. Coral reefs, already stressed by warming and acidification, bleach completely and die, their symbiotic algae unable to photosynthesize in the suffocating darkness. Kelp forests wither and collapse, their towering fronds dissolving into the black water like ghosts. The die-off is biblical in scale, a mass extinction event that transforms the ocean from a vibrant garden into a graveyard. Yet even as billions of organisms perish, something remarkable begins to happen in the spaces between the death. Life, as it has done countless times before, refuses to accept extinction. Chemosynthetic bacteria, once confined to hydrothermal vents and cold seeps, suddenly find their moment. These microorganisms don't need sunlight because they harvest energy from chemical reactions, breaking down hydrogen sulfide, methane, and other compounds seeping from the ocean floor. As the photosynthetic world collapses, chemosynthetic communities begin to expand, creeping upward from the deep ocean like an underground resistance movement finally coming to the surface. They form bacterial mats on the seafloor, cloudy blooms in the water column, symbiotic partnerships with desperate survivors. For animals that can adapt quickly enough, these bacteria offer a lifeline, a new foundation for ecosystems in the absence of the sun. But adaptation on this scale doesn't happen overnight. Evolution operates on geological timescales, grinding through generations, testing mutations, discarding failures. The question becomes, can any surface-dwelling species evolve fast enough to survive in this new darkness? Or will the ocean become a realm inhabited only by those creatures already adapted to lightless depths? Consider the plight of a predatory fish, something like a tuna or a mackerel, engineered by millions of years of natural selection to be a visual hunter. Its large eyes, its streamlined body built for high-speed chases, its entire neural architecture designed to process visual information. All of this becomes not just useless but a liability. Maintaining eyes requires enormous metabolic energy, and in a world where food has become desperately scarce, every calorie matters. Individuals born with smaller eyes, with reduced visual processing centers in their brains, suddenly have an advantage because they waste less energy on organs that serve no function. Over dozens, hundreds, thousands of generations, the eyes shrink, the optic nerves atrophy, the brain regions dedicated to vision get repurposed. But here's the terrifying realization. Evolution doesn't just erase what doesn't work. It builds something new. As vision fades, other senses must compensate, must expand beyond their original limits. The lateral line system, which detects pressure changes and water movements, becomes exquisitely sensitive. The olfactory organs grow larger, more complex, capable of detecting chemical signatures at parts per trillion. And then there's the sense that will come to dominate this new ocean, the ability to perceive and produce light without eyes. Bioluminescence is not a new invention. Roughly 76% of ocean animals already possess this ability, using bacterial symbiosis or their own chemistry to produce light for various purposes. But in the permanently dark surface ocean, bioluminescence transforms from an occasional trick into the primary language of life. The first adaptations are defensive, prey species evolving brighter, more startling light displays to shock and disorient predators during attacks. A cloud of luminescent ink, evolved from squid ancestors, becomes a smoke screen of light. Counterillumination, previously used by twilight zone species to blend with downwelling sunlight, gets repurposed as camouflage against the bioluminescent background glow of other organisms. Within a few thousand generations, species that never glowed before begin to develop light organs through convergent evolution, driven by the desperate need to communicate in the darkness. Mating displays become elaborate light shows, males and females flashing species-specific patterns to find each other in the void. Schools of fish coordinate their movements through synchronized bioluminescent pulses, creating waves of light that flow through the black water like aurora borealis beneath the sea. But here is where mystery deepens into something darker, something that suggests the horror lurking at the edge of adaptation. Predators don't just watch this explosion of bioluminescence from the sidelines. They evolve to exploit it, to weaponize light itself against their prey. Some species develop the ability to mimic the bioluminescent patterns of prey animals, becoming living lures that draw victims close before striking. Others evolve light-sensitive patches on their skin, not true eyes, but simple photoreceptors that can detect the direction and intensity of bioluminescent flashes, allowing them to hunt despite having no proper vision. Most disturbing are the predators that evolve to produce no light of their own, becoming true creatures of darkness that hunt the glowing prey around them. They are invisible, moving through the ocean as absence, as negative space, detectable only by the sudden extinguishing of bioluminescence as they pass. Imagine being one of those glowing prey fish, surrounded by what looks like constellations of your fellows, never knowing which lights are real and which are traps, never seeing the dark shapes that slide between the stars. The ocean begins to stratify in ways that have no precedent in Earth's history. The surface, once the richest zone, becomes a transitional layer where bioluminescence wars with darkness and evolution experiments with radical new forms. Deeper waters, already adapted to lightlessness, see an influx of refugees from above, species forced downward by starvation, competing with deep-sea specialists in their own territory. Some surface species manage this transition. Their descendants, compressed by selection pressure, become smaller, slower, more energy efficient, gradually taking on the characteristics of deep-sea life. Others, unable to compete in the depths and unable to survive the barren surface, simply vanish, entire lineages erased. But there are also species that find niches in the new darkness. Animals that would never have survived in the sunlit ocean but now flourish. Jellyfish, with their low metabolic requirements and their ability to survive on scarce food, bloom in massive numbers. Certain bacterial symbionts, offering their chemosynthetic abilities to host animals, become the new chloroplasts, the new basis for complex multicellular life. The ocean is being rewritten from the bottom up. As the first few 100,000 years pass, the pace of visible change slows, but beneath the surface, evolution continues its relentless work. Genetic mutations accumulate, gene regulatory networks get rewired, developmental pathways diverge. What emerges is not just an adaptation to darkness but a fundamental reimagining of what it means to be a marine organism. The creatures swimming in these black waters are no longer recognizable as descendants of their sunlit ancestors. They sense the world through modalities we can barely comprehend, navigating by electromagnetic fields, by chemical trails invisible to us, by pressure waves and electrical impulses. They have transcended vision, leaving it behind as an evolutionary dead end, and in doing so, they've accessed dimensions of perception that sighted animals never could. This is the ocean without end, the permanent night, and it is more alive than we ever imagined possible. But what we haven't yet discussed is how these creatures will refine their non-visual senses to even greater extremes, creating hunters and hunted locked in sensory arms races beyond anything evolution has produced before. The darkness is not empty. It is waiting, full of invisible eyes that see without seeing, and the real terror is about to begin. In the permanent darkness of the surface ocean, light has become more than just a tool for survival. It has become language itself, the primary medium through which life communicates, negotiates, and deceives. Within a few 100,000 years of the sun's disappearance, bioluminescence transforms from a curiosity possessed by scattered species into a universal trait shared across nearly every mobile organism. The ocean at night, if we could still call it night when there is no day, pulses with countless points of light, creating a living constellation map that shifts and flows with the currents. Each flash, each glow, each sustained pulse carries meaning, but what kind of meaning? Species-specific recognition patterns allow individuals to find their own kind in the darkness. Intricate courtship displays advertise fitness and genetic quality. Warning flashes signal toxicity or danger to potential predators. The language of light is rich, complex, and utterly alien to surface-dwelling minds. But as with any language, once it becomes widespread enough, it also becomes vulnerable to those who would speak false words for their own gain. Consider the evolution of mating displays in this perpetually dark world. Fish that once relied on coloration, on the shimmer of scales catching sunlight, on elaborate fins displayed in courtship dances, must now translate all of that visual information into patterns of light. Males develop photophores, specialized light-producing organs, arranged in species-specific configurations along their bodies. A courting male might flash these organs in rhythmic sequences, creating temporal patterns as distinctive as a signature. Some species evolve slow, pulsing waves of light that travel along their flanks, while others produce rapid stroboscopic bursts that seem to freeze time itself. Females, equipped with eyes adapted to detect these precise wavelength ranges, can distinguish their own species' patterns from all others, even when dozens of different species are displaying simultaneously in the same water column. This should be elegant, a beautiful solution to the problem of finding mates in darkness. But evolution is never content with elegance alone. Within this communication system, the seeds of something darker have already begun to germinate. Predators watch these mating displays with interest that goes far beyond mere observation. A female fish, displaying her receptive pattern, broadcasting her location and willingness to mate, is advertising vulnerability. She is announcing that she is distracted, focused on reproduction rather than survival, an ideal target. The first predators to evolve mimicry of these mating signals gain an enormous advantage, becoming living lures that draw prey directly to them. These mimics don't need to be perfect replicas. They only need to be convincing enough to trigger approach behavior in their victims. A predatory anglerfish descendant evolves a specialized photophore that can produce multiple flashing patterns, cycling through the courtship signals of various prey species. When a male approaches, expecting a mate, he finds death instead. The evolutionary pressure this creates is immense. Prey species must now not only recognize their own kind but also distinguish between genuine displays and predatory deceptions. The mating signals become more complex, incorporating temporal elements, intensity variations, even polarization patterns that are difficult for mimics to replicate perfectly. But predators evolve in response, their mimicry growing ever more sophisticated in an endless arms race. The proliferation of bioluminescent communication creates an unexpected problem that no evolutionary pressure could have predicted during the sunlit era. Light noise. When every organism in the water column is producing light for various purposes, the ocean becomes a chaos of overlapping signals, a sensory environment so cluttered that distinguishing meaningful patterns from background static becomes nearly impossible. Imagine trying to have a conversation in a room where hundreds of people are simultaneously shouting, flashing strobe lights, and projecting visual patterns onto every surface. This is the reality facing marine organisms in the bioluminescent ocean. Species that produce simple, easily recognized patterns find their signals drowned out by the complexity around them. Those that evolve more elaborate displays to stand out contribute even more to the overall noise. The system threatens to collapse under its own success, creating selection pressure for organisms that can either cut through the noise or abandon light-based communication altogether. Some species evolve the ability to produce light in unusual wavelength ranges, shifting into the far blue or even ultraviolet portions of the spectrum where fewer competitors operate. Others develop temporal filtering in their visual systems, learning to ignore steady light sources and respond only to specific flashing frequencies. But the most disturbing adaptation emerges in predators that have learned to exploit the light noise itself. These hunters don't produce light of their own, or if they do, it's minimal and carefully controlled. Instead, they position themselves within clouds of bioluminescent organisms, using the ambient glow as illumination to hunt by. They are shadows within light, negative spaces that move through the glowing waters like holes in reality. Prey animals, their attention fixed on the complex light displays around them, fail to notice the dark shapes until it's too late. Some of these shadow hunters evolve skin pigmentation that actively absorbs light, making them appear as voids even when directly illuminated by bioluminescent flashes. They become the anti-light creatures defined not by what they produce but by what they consume. This creates a terrifying dynamic where producing light, once a survival advantage, becomes a liability that illuminates prey for these invisible predators. The ocean stratifies into lit zones, where bioluminescent communication dominates, and dark zones, where these shadow hunters prowl the boundaries, waiting for their glowing prey to stray too close. Evolution, faced with the chaos of light noise and the threat of shadow predators, begins to explore radical solutions that border on the incomprehensible. Some species develop active countermeasures against both problems simultaneously. They evolve the ability to produce not just light but coordinated light, schooling behaviors where hundreds or thousands of individuals synchronize their bioluminescent displays into massive, coherent patterns. These living light shows serve multiple purposes at once: the sheer intensity cutting through background noise, the synchronized pulses making it difficult for shadow predators to target individuals, the complex patterns conveying information on a scale impossible for lone organisms. Marine biologists from the sunlit era would recognize elements of this behavior in firefly swarms and certain shallow water squids, but never at this scale or level of sophistication. Entire schools flash in unison, creating waves of light that propagate through three-dimensional space, geometric patterns that emerge from simple rules followed by thousands of individuals. But here's the question that should disturb us. If these patterns emerge from simple individual behaviors, from each animal responding to the flashes of its neighbors, then what happens when a predator learns those same simple rules? The answer reveals itself in one of the most unsettling phenomena in the dark ocean. Predatory schools, descended from social hunters, begin to infiltrate the synchronized light displays of their prey. At first, they simply position themselves within prey schools, using the cover of coordinated flashing to hide their approach. But over generations, they evolve the ability to match the timing of prey bioluminescence, to participate in the synchronized displays, to become indistinguishable from the prey themselves until the moment of attack. These infiltrator predators move through prey schools like wolves in sheep's clothing, or perhaps more accurately, like cells of an immune system that has learned to evade recognition. They flash when their prey flash, go dark when their prey go dark, and when the moment is right, they strike from within. The prey have no defense against this because the predators are speaking their language perfectly, using the very communication system meant to provide safety. This drives the evolution of increasingly complex recognition systems, individual identification markers layered onto the collective displays, but predators evolve in response, and the arms race spirals into realms of complexity that strain the computational capacity of nervous systems to maintain. As the age of bioluminescence reaches its peak, perhaps 1 million years into the permanent darkness, the ocean has become something that would be utterly alien to any observer from the sunlit past. Light is everywhere yet means nothing. Every flash a potential truth or lie, every pattern a message or a trap. The energetic cost of maintaining bioluminescent systems, of processing the overwhelming sensory input, of constantly updating recognition patterns to stay ahead of mimics, begins to outweigh the benefits. Selection pressure builds for alternatives, for sensory modalities that can't be seen or mimicked by those who rely on vision alone. Some species begin to reduce their bioluminescence, using it more sparingly, relying increasingly on other senses. Others double down, creating ever more elaborate light organs and visual processing systems, committing fully to the language of light even as it becomes corrupted by deception. But there are organisms, quiet and unnoticed in the chaos of light, that have been evolving along an entirely different path. They hunt not by what they see but by what they feel, by detecting the electromagnetic and pressure signatures of their prey. They are the future, and they move through the ocean like ghosts, invisible to eyes adapted to a world of light. The age of bioluminescence is ending, not because it failed, but because it succeeded too well, creating a sensory environment so complex that it became its own barrier to survival. What comes next will make the language of light seem simple by comparison. There is a sense that evolution perfected long before the darkness came, a sense that operates in realms invisible to eyes, a sense that detects the fundamental electrical nature of life itself. Electroreception. Every living cell generates tiny electrical potentials as ions move across membranes, as muscles contract, as hearts beat, as neurons fire. In the sunlit ocean, this sense was the private domain of sharks, rays, and a handful of other specialized hunters equipped with organs called ampullae of Lorenzini. These gel-filled pores, connected to sensory cells via conductive jelly more efficient than most human-made semiconductors, could detect electrical fields as weak as 5 nanovolts per centimeter. To put this in perspective, if 2 standard batteries were connected 1,000 miles apart in the ocean, a shark could detect when one of them died. This ability allowed them to find prey buried in sand, to navigate using Earth's magnetic field, to sense the living electromagnetic landscape of the ocean. But in the permanently dark surface waters, where bioluminescence has become corrupted by mimicry and noise, electroreception suddenly offers advantages that vision never could. You cannot fake a heartbeat. You cannot mimic the electrical signature of life without being alive yourself. Or so evolution believed, for a time. The first species to evolve enhanced electroreception in the dark ocean are descendants of those ancient specialists, the sharks and rays that already possessed the basic machinery. But the selection pressure in this new environment drives modifications that would have seemed impossible in the sunlit past. The number of ampullae increases dramatically, spreading from concentrated clusters on the head to distributed networks covering the entire body surface. Each ampulla becomes more sensitive, the jelly more conductive, the sensory cells more responsive. Within a few 100,000 generations, these electroreceptive predators can detect a prey fish's heartbeat from 300 meters away in complete darkness. They can sense the muscle contractions as prey attempts to swim silently through the black water. They can even detect the neural activity in a prey animal's brain, the electrical cascade of decision-making that precedes movement. Imagine being that prey fish, frozen in the darkness, knowing that any thought of escape, any impulse to flee, generates an electrical signature that announces your intention to predators before you even move. The ocean becomes a place where thinking itself is dangerous, where consciousness is a liability. But electroreception is not limited to the descendants of sharks. Convergent evolution, that remarkable phenomenon where unrelated species independently develop similar solutions to similar problems, begins to manifest across multiple lineages. Fish species that had no electroreceptive abilities in the sunlit ocean start to evolve their own versions of the sense, using different molecular mechanisms but achieving the same functional result. Some develop modified lateral line organs, the pressure sensing system that all fish possess, adapting them to detect electrical fields instead of or in addition to mechanical vibrations. Others evolve entirely novel structures, specialized epithelial cells that concentrate charged proteins in ways that make them sensitive to tiny voltage differences. The molecular pathways are different, the anatomical structures are different, but the end result is the same: the ability to perceive the electrical dimension of reality. Within 2 million years of the darkness beginning, electroreception has spread through the ocean's fauna like wildfire, becoming as ubiquitous as vision once was. The electromagnetic spectrum of life becomes the new visible spectrum, the primary modality through which organisms perceive their world. This creates an arms race more sophisticated than anything the age of bioluminescence produced. Prey species, faced with predators that can detect their bioelectric fields from hundreds of meters away, begin to evolve countermeasures that seem to belong more to electronic warfare than to biology. Some species develop the ability to reduce their electrical signature, evolving specialized muscle tissues that contract with minimal ion movement, hearts that beat in patterns designed to minimize electromagnetic emissions. Others take a different approach, evolving what can only be described as biological jamming systems. These prey fish develop electric organs, similar to those found in electric eels but used defensively rather than offensively, that generate random electrical noise. When threatened, they activate these organs, flooding the local environment with electromagnetic static that masks their true bioelectric signature. Predators, their electroreceptive systems suddenly overwhelmed by noise, lose track of their prey in the chaos. But this defense mechanism has a cost, requiring enormous energy expenditure, and prey can only maintain it for short periods before exhaustion sets in. The most disturbing evolution occurs in species that develop what biologists from the sunlit era would have called electrical camouflage, though that term barely captures the sophistication of what emerges. These organisms evolve the ability to actively generate counterfields, electrical patterns that precisely cancel out their own bioelectric emissions. It's the electromagnetic equivalent of noise-canceling headphones, but implemented in living tissue. Specialized electric organs detect the organism's own heartbeat, muscle contractions, and neural activity, then generate inverse electromagnetic waves that destructively interfere with these signals. To an electroreceptive predator, these camouflaged prey simply disappear, becoming electromagnetic voids that register as empty water. The energy cost is staggering, requiring metabolic rates that would have been unsustainable in the food-scarce early dark ocean. But as chemosynthetic ecosystems mature and energy becomes more available, this strategy becomes viable. Some species take electrical camouflage even further, evolving the ability to generate false signatures that mimic rocks, debris, or even other species. The electromagnetic landscape becomes as deceptive as the bioluminescent one ever was, filled with ghosts and illusions that make distinguishing reality from fabrication nearly impossible. Predators respond to these challenges not by evolving even more sensitive electroreception, though that happens too, but by developing collective hunting strategies that exploit the networked nature of electromagnetic communication. Social species, descended from schooling fish and cooperative hunters, evolve the ability to share electroreceptive information across entire groups. Each individual acts as a sensor node in a distributed detection grid, its brain processing local electrical data and communicating findings to neighbors through specialized electrical pulses. The group mind that emerges from this network is capable of processing electromagnetic information across a volume of ocean far larger than any individual could monitor. These coordinated predators can triangulate prey locations from multiple sensor positions simultaneously, defeating electrical camouflage by detecting the minute inconsistencies that even the best counterfields can't perfectly eliminate. They hunt as a unified organism, their individual identities subsumed into a collective consciousness held together by electromagnetic bonds. When one member of the pack detects prey, all members know instantly, their attack perfectly synchronized without any visible or audible signal. The most terrifying aspect of these hive-mind hunters is their ability to sense the internal state of their prey in ways that go beyond mere location. The electrical activity of a brain under stress, experiencing fear, differs measurably from a calm brain. These predators evolve to recognize these patterns, to read emotion directly from electromagnetic signatures. They can sense when prey has detected them, when panic sets in, when the prey's nervous system shifts from normal function to fight or flight response. Some predator species learn to exploit this, deliberately revealing their presence to induce fear, then tracking the terrified prey by its panic-elevated bioelectric signature, even if it attempts to flee using electrical camouflage. It's psychological warfare at a cellular level, predators that hunt not just bodies but minds, that weaponize their prey's own fear against them. The ocean becomes a place where nowhere is safe, where the very act of being alive, of having a functioning nervous system and beating heart, makes you visible to horrors that slip through the darkness, reading your terror like a beacon. Yet even as electroreception reaches these nightmarish extremes of sophistication, its fundamental limitations begin to create pressure for alternatives. Electricity, for all its advantages, travels poorly through water, its range limited by the conductivity of seawater and the inverse square law that governs all electromagnetic radiation. In the vast open ocean, even the most sensitive electroreceptors have a maximum effective range of perhaps a kilometer under ideal conditions, often much less in areas with strong currents or thermal gradients that distort electrical fields. This creates ecological niches for organisms that can operate beyond this range, for senses that can reach across tens or hundreds of kilometers. Some species begin to enhance their mechanoreceptive systems, the pressure-sensing organs that detect water movement and vibrations. Others evolve increasingly sophisticated chemical detection, following scent trails through the dark water. But the sense that will come to dominate the next phase of evolution, the sense that will prove to be the ultimate tool for perceiving the dark ocean, is one that uses the water itself as a medium: sound. In the permanent darkness, sound can travel hundreds of kilometers, carrying information that light and electricity never could. And in the depths where pressure makes every movement audible, where silence is the only true camouflage, evolution is about to create hunters that can hear your heartbeat from the other side of the ocean. Sound travels through water at roughly 1,500 meters per second, 5 times faster than it moves through air, and it can propagate across entire ocean basins with minimal degradation. Low-frequency sounds, the deep rumbles and pulses that resonate through the abyss, can traverse thousands of kilometers, carrying information across distances that would take days to swim. In the permanently dark ocean, where light penetrates nothing and electrical fields fade within a kilometer, sound becomes the sense of distance, the only way to perceive the world beyond your immediate surroundings. Evolution, having exhausted the possibilities of bioluminescence and pushed electroreception to its limits, turns its attention to acoustic systems with an urgency born of necessity. Species that already possessed hearing organs find those structures expanding, becoming more sensitive, more sophisticated, more capable of extracting information from the vibrations that fill the water. Within a few million years of the darkness beginning, the ocean transforms into a three-dimensional soundscape where every movement, every heartbeat, every breath creates ripples in the acoustic fabric of reality. But sound is not just a medium for communication. It is a weapon, a shield, and a window into dimensions of perception that make the previous sensory modalities seem primitive by comparison. The evolution of extreme hearing begins with the lateral line, that ancient sensory system present in all fish, a series of pressure-sensitive cells running along the body that detect water movements and low-frequency vibrations. In the dark ocean, these organs proliferate and specialize, covering ever larger portions of the body's surface, developing the ability to discriminate between frequencies with remarkable precision. Some species evolve inner ear structures of extraordinary complexity, with multiple chambers tuned to different frequency ranges, effectively creating biological spectrum analyzers that can decompose complex sounds into their constituent components. The most extreme adaptations appear in predators that evolve the ability to detect and interpret infrasound, frequencies below the threshold of human hearing, which travel extraordinary distances through water. These hunters can hear the muscle contractions of prey hundreds of kilometers away, can detect the approach of storms by the infrasonic signatures they generate, can sense geological events on the other side of the ocean. But the true revolution comes when species evolve not just to hear sound but to produce it with unprecedented control and precision, to use sound not passively but actively, as a tool for illuminating the darkness. Active echolocation, once the domain of dolphins and toothed whales, spreads through the ocean's fauna like wildfire. Species that never possessed this ability in the sunlit era begin to evolve sophisticated sound-producing organs, modified swim bladders, and specialized muscle groups that can generate clicks, pulses, and complex acoustic waveforms. These organisms emit sounds and listen to the echoes that return, building mental maps of their surroundings from pure acoustic information. The sophistication of these systems rivals and eventually surpasses anything that existed before the darkness. Predators evolve the ability to adjust the frequency of their echolocation based on target distance and environmental conditions, using high-frequency clicks for detailed close-range imaging and low-frequency pulses for long-range detection. The resolution of their acoustic vision becomes extraordinary, capable of distinguishing between species based on the subtle differences in how sound reflects off their bodies. Some predators develop echolocation so advanced they can detect prey buried in sediment, can identify individual organisms within densely packed schools, can even perceive the internal anatomy of their targets. This last ability is perhaps the most disturbing development in the age of sound. Imagine being transparent to sound, your internal organs visible to any creature capable of interpreting the echoes that return from within your body. Acoustic predators evolved to do exactly this, using high-frequency sonar pulses that penetrate tissue and reflect differently off bone, muscle, organs, and gas-filled spaces. They can identify prey species not just by external shape but by internal structure, can assess health and nutritional value before attacking, can target specific organs during predation. Some species develop the ability to detect pregnancy by the acoustic signature of developing embryos, to identify sick or injured individuals by the abnormal sounds produced by damaged tissues. The ocean becomes a place where privacy doesn't exist, where the interior landscape of your body is as visible as your surface would have been in the sunlit era. Prey species attempt to evolve countermeasures, developing bones and tissues with acoustic properties that minimize internal reflections. But there's only so much that evolution can do when the fundamental physics of sound propagation make concealment nearly impossible. The arms race shifts from hiding your presence to accepting visibility and instead focusing on deception and defense through other means. The most successful defensive adaptation against acoustic predation is perhaps the most elegant solution evolution has yet produced in the dark ocean. Sound-absorbing skin. Certain prey species evolve epithelial layers incorporating structures that function like the anechoic tiles used on stealth submarines, containing thousands of microscopic air pockets arranged in patterns that trap and dissipate incoming sound waves rather than reflecting them. When echolocating predators scan these organisms, the returning echo is so weak as to be nearly undetectable, creating acoustic shadows, holes in the predator's perception where prey should be visible but simply aren't. The energy cost of maintaining these structures is significant, the air pockets requiring constant biological maintenance to prevent collapse under pressure, but the survival advantage is enormous. These acoustic ghosts move through the ocean leaving almost no trace, detectable only through secondary cues like the water displacement their movement creates. Predators respond by evolving even more powerful echolocation systems, increasing transmission power and refining reception sensitivity, but there are physical limits to how loud an organism can safely broadcast without damaging its own hearing organs or revealing its position to every other creature within range. As acoustic warfare escalates, some species evolve strategies so sophisticated they border on the incomprehensible. Sonic camouflage, analogous to the electrical camouflage that emerged in the previous epoch, allows organisms to actively manipulate their acoustic signature. These creatures evolve sound-producing organs that can generate anti-echoes, acoustic waveforms that destructively interfere with incoming echolocation pulses, effectively canceling out the sounds that would reveal their presence. Others evolve the ability to mimic the acoustic signatures of inedible objects, their bodies producing echoes that make them appear to predators as rocks, coral fragments, or pieces of debris. The most disturbing development is acoustic identity theft, where prey organisms evolve to replicate the echolocation signatures of predators, making themselves appear dangerous to would-be attackers. The acoustic environment becomes as deceptive as the bioluminescent one ever was, filled with false signals and phantom presences. Trust becomes impossible when you cannot verify that the sounds you hear correspond to reality. But while deception flourishes, there is one strategy that cannot be faked, one defense that works against all acoustic predators: absolute silence. Silence, in the ocean of sound, is the ultimate camouflage. Species evolve to minimize every acoustic emission, developing hearts that beat with carefully controlled rhythms designed to minimize pressure pulses, respiratory systems that exchange gases without creating bubbles or turbulence, movement strategies that disturb the water as little as possible. These silent swimmers become nearly invisible to acoustic predation, but achieving true silence requires behavioral adaptations as extreme as the morphological ones. Silent prey must move slowly, cannot flee from predators because rapid movement generates too much noise, cannot feed on hard-shelled organisms because crushing shells create sound. They exist in a state of perpetual stillness, frozen in the water column, waiting for opportunities to feed or mate that must be executed with glacial slowness to maintain acoustic invisibility. Yet even silence has its limits. Parasites evolve to exploit these motionless prey, attaching themselves to hosts and mimicking their acoustic signatures so perfectly that they become undetectable. These acoustic parasites spread through populations like invisible plagues, each infected individual unknowingly carrying additional organisms that produce no sound of their own, living as perfect acoustic shadows of their hosts. When these parasites finally reveal themselves, reproducing or moving to new hosts, the acoustic burst can attract predators, dooming the original host to detection and death. The ocean at the height of the acoustic age is a place of such sensory complexity that describing it in terms familiar to surface-dwelling minds becomes nearly impossible. Every organism is simultaneously broadcasting and receiving, creating and interpreting, deceiving and being deceived. The soundscape is layered, three-dimensional, constantly shifting as currents and temperature gradients bend sound paths in unpredictable ways. Thermoclines create acoustic mirages, layers where sound speed changes abruptly, causing echolocation pulses to refract and reflect in ways that make distant objects appear close and nearby objects seem far away. Deep scattering layers, concentrations of organisms that reflect sound so effectively they appear on sonar as false seafloors, create acoustic barriers that predators must learn to distinguish from real geological features. Some species evolve the ability to use these natural acoustic phenomena strategically, hiding in thermal boundaries or positioning themselves within scattering layers to avoid detection. But as sophisticated as sound-based perception has become, it too has fundamental limitations. Sound cannot reveal chemical composition, cannot detect static objects that produce no acoustic signature, cannot penetrate certain materials or propagate effectively in areas of extreme turbulence. The stage is set for the emergence of something unprecedented, the fusion of all sensory modalities into unified perception systems that will transcend the limitations of any single sense. The age of sound is ending, not because sound has failed, but because evolution has discovered something even more powerful: synesthesia as a survival strategy. Before trying to imagine the strangest hunters of this endless night ocean, it helps to realize that evolution rarely stops at a single trick when survival is on the line. At first, creatures tried sight, then light, then electricity, then sound, each new sense rising to dominance and then running into its own hard limits. Eventually, in this permanently dark sea, the most successful lineages are not those that specialize in a single supersense, but those that begin to fuse all of them into something new. Instead of having separate channels for light, pressure, sound, chemicals, and electrical fields, their nervous systems start to treat all incoming data as one blended stream. Imagine perceiving the world as a single seamless experience where a distant heartbeat, a faint chemical trail, and a tiny pressure ripple feel like different colors of the same sensation. For these synesthetic hunters, there is no distinction between hearing and feeling, between smelling and seeing, between detecting electricity and sensing motion. Everything arrives at once as a unified map, rich and terrifyingly detailed. In a realm where any single sense can be fooled, their advantage is simple and profound. It is almost impossible to lie to all of their senses at the same time. The transformation begins deep inside the brain, long before it manifests in visible anatomy. Early on, different senses have their own compartments, little processing islands devoted to vision, hearing, chemoreception, and so on. Over evolutionary time, the borders between these islands begin to erode, and new regions emerge where signals from multiple senses converge and are processed together. Neurons that once responded only to sound begin to fire in response to the combination of sound and pressure, or sound and electrical fields, or even sound and the faint glow of bioluminescence. At first, this integration simply sharpens detection, letting animals confirm that a stimulus is real by cross-checking it through multiple channels. But as this architecture becomes more elaborate, something stranger occurs. The brain stops treating these inputs as separate at all. For a synesthetic predator, a movement in the water is not just a ripple. It has a taste, a faint electric flavor, a ghostly acoustic outline. Every event in the environment carries a multisensory signature that feels like a single, complex sensation. When such a creature turns its attention toward you, it does not merely detect that you are there. It experiences you as a pattern woven from many threads, impossible to mistake for anything else. On the outside, these hunters look like living sensor arrays, their bodies studded with specialized organs tuned to different aspects of the dark ocean. Along their flanks run dense rows of mechanoreceptive hairs, each one capable of detecting minuscule vibrations from many body lengths away. Embedded in the skin are clusters of electroreceptive pores, sensitive enough to register the weak fields produced by a single twitch of your muscles. Deeper beneath the surface lie networks of pressure-sensitive cavities and fluid-filled canals that act like internal microphones, tuned to a wide range of frequencies. Bioluminescent organs still exist, but they have shifted from simple communication tools to carefully controlled probes, flickering in ultra-short flashes to test how nearby bodies reflect and scatter light. Even the chemical senses have expanded, with folds of sensory epithelium that can read gradients of dissolved compounds as if they were maps of recent activity. Each of these structures on its own would already be impressive, but it is their coordination that makes them unsettling. Every organ samples the same event from a different angle, feeding its fragment to a central system that stitches them together into a single, eerily clear perception of reality. The result is a form of awareness that might feel, to us, like seeing and hearing and touching all at once, extended into dimensions we have no words for. When a synesthetic hunter moves through the water, it is constantly projecting and receiving, probing and listening, tasting and feeling the fabric of its surroundings. A distant school of prey is not just a cluster of moving shapes. It becomes a shimmering knot of overlapping pressure disturbances, chemical traces, heartbeats, and echo returns. The predator can sense which individuals are hungry by the chemistry of their exhaled waste, which are injured by the irregularity of their movements, which are anxious by the jittering patterns in their electrical activity. It can tell which way the school is likely to turn before they decide, because it reads intention as subtle shifts across multiple sensory channels. In a sense, these creatures do not track where prey are. They track where prey will be, anticipating trajectories from the fused stream of data pouring into their nervous systems. To ask whether they see you or hear you or feel you is to misunderstand their reality. To them, you simply exist as a dense, living signal in a dark sea of weaker ones. With this level of perception, their hunting style looks less like a chase and more like the unfolding of a carefully choreographed inevitability. A synesthetic predator rarely needs to sprint after its prey. It already knows which escape paths are viable and quietly moves to cut them off before the prey even begins to flee. It glides into positions that to us would seem arbitrary, but to it feel perfectly aligned with the invisible flows of sound, chemicals, pressure, and electricity. When it finally accelerates, the attack is brief and almost anticlimactic, as if the outcome had been decided long before the first movement. Prey animals try the tricks that once saved them from single-sense hunters. Bioluminescent flashes to confuse, electric jamming to overload, sonic bursts to stun. But a multisensory brain merely downgrades one corrupted channel and leans more heavily on the others, much like a human ignoring static-filled audio while reading subtitles on a screen. Even silence and stillness, once the ultimate defense, become less effective, because the predator can still follow the fading chemical wake left behind or the residual disturbances in the water. It is as if the ocean itself whispers to these hunters where everything has been and where everything is going. Of course, evolution does not grant such terrifying abilities without cost, and the price is paid in energy and vulnerability of a different kind. Maintaining large, complex brains and dense sensory arrays demands enormous amounts of fuel in an ecosystem where food is still scarce and competition is fierce. These predators must feed less like casual hunters and more like strategic planners, targeting high-value prey and minimizing wasted effort. Their developmental processes become fragile, easily disrupted by environmental changes that affect nutrient availability or temperature. Some lineages grow increasingly specialized, tuned so precisely to a particular combination of sensory cues that even small shifts in ocean chemistry or background noise can disorient them. Others begin to offload part of the sensory burden onto their social structures, forming groups where information is shared between individuals, but that brings its own risks of dependency and confusion. Still, as long as energy flows through the dark ocean, this integrated sensory strategy remains one of the most powerful known. It is a precarious balance. Tremendous power, balanced on a knife edge of complexity. Perhaps the most unsettling aspect of these synesthetic hunters is their relationship to something like emotion, or at least to internal states in other organisms. When multiple senses converge on a single target, They pick up not just position and motion, but numerous subtle markers of physiological state. A sudden spike in heart rate, a shift in hormone-related chemicals excreted across the gills, a quiver in muscle tension, a tiny change in breathing rhythm. All of these fold together into a recognizable pattern. Over evolutionary time, predators learn to associate certain multisensory signatures with fear, fatigue, confusion, or confidence, and they act accordingly. They may ignore confident groups that are alert and ready, and instead focus on a single anxious straggler whose body broadcasts stress like a beacon. In this way, they become connoisseurs of vulnerability, selecting not just any prey, but the most psychologically exposed. It raises a chilling question. What does the world feel like to a creature that experiences emotion in others as a tangible, almost physical texture in the water around it? In their presence, even your fear is not private. It is simply another color added to the portrait they perceive. By the time this age of synesthetic hunters reaches maturity, the ocean has become a place where information itself is the ultimate currency of survival. Every organism, from microscopic drifters to massive predators, contributes to and navigates a dense web of overlapping signals. The creatures that dominate are not those with the strongest jaws or fastest fins, but those that can best read and rewrite this invisible tapestry. And yet, for all their power, these apex predators remain just one branch on the sprawling tree of life in the eternal night. In other corners of the dark ocean, very different experiments are unfolding. Colonial networks of smaller organisms sharing sensory duties, strange filter feeders that use multisensory fusion not to hunt, but to synchronize with the chemical and acoustic rhythms of entire ecosystems. The story of senses in this world is not just a tale of hunters and hunted, but of perception itself stretching into new shapes. Standing at the edge of this abyss, imagining a mind that lives inside such a storm of integrated signals, we are forced to confront a humbling thought. In an ocean where sight has long since died, the real mystery is not what is hidden in the darkness, but how much more there is to perceive than human senses ever allowed us to know. After tens of millions of years in perpetual darkness, the surface ocean has completed its transformation from sunlit paradise to alien realm, a thriving biosphere built not on photosynthesis, but on the patient chemistry of the deep earth. Chemosynthetic bacteria, those microscopic engineers that convert hydrogen sulfide, methane, and dissolved minerals into energy, have become the new foundation of life, forming vast mats across the seafloor and blooming in water columns where chemical gradients persist. Animals that once chased sunlight-adapted prey now filter these bacterial clouds, their guts teeming with symbiotic microbes that extend their reach into previously toxic environments. Giant tube worms, evolved from vent specialists, colonize continental shelves, their red plumes waving in currents that carry chemical riches from below. The food web inverts completely, with primary production happening not at the sunless surface but rising from abyssal depths, creating biomass flows that support predators larger and more abundant than anything the sunlit ocean ever sustained. Ecosystems pulse with life organized around chemical seeps, hydrothermal gradients, and organic detritus raining from decaying surface layers. What was once barren has become bountiful, but in ways that defy every expectation of ocean ecology. The darkness has not killed the sea. It has reborn it as something profoundly other. Deep-sea generalists, creatures long adapted to pressure and dark, now migrate upward in massive numbers, claiming territories once dominated by fragile surface species. Anglerfish descendants, with their bacterial lures and cavernous stomachs, prowl midwater realms once filled with frantic schools of visual hunters. Glass squid, transparent and nearly invisible even to advanced senses, expand their range into sunless shallows, their bodies perfect for ambush in a world of multisensory detection. These upward colonists bring strategies honed over eons in the abyss. Extreme metabolic efficiency, gigantism in low-food niches, reproductive strategies that bet everything on rare massive spawnings. They outcompete holdover surface lineages not through speed or aggression, but through sheer endurance, their physiologies tuned to environments where energy conservation trumps all else. Vast migrations now follow chemical trails rather than plankton blooms, seasonal pulses of nutrient upwelling drawing billions of organisms into synchronized movements across entire ocean basins. The surface layer, once a thin photic zone, thickens into a chemocline where bacterial production fuels filter feeders the size of whales. In this inverted ecology, the old deep-sea rule applies everywhere. Bigger is better when food is unpredictable and predators lurk in every shadow. The true survivors, however, are not the aggressive hunters or the opportunistic colonists, but the perceptive ones, organisms whose multisensory integration has reached levels of refinement that border on precognition. These are the species that read the ocean not as fragmented signals, but as a unified symphony of chemical gradients, pressure waves, electrical pulses, and acoustic resonances. They perceive migrations before they begin, sensing the collective hormonal shifts in distant populations, the electromagnetic precursors of spawning aggregations, the infrasonic rumbles of tectonic activity that will reshape seafloor chemistry. Their nervous systems, vast and distributed, process this information not for immediate predation but for long-term survival strategy, positioning themselves at the convergence of multiple food flows before competitors arrive. In a world where every sense can deceive, their success lies in relentless cross-verification, dismissing false signals through the weight of contradictory evidence from multiple channels. They become the architects of ecosystems, their behaviors creating predictable patterns that other species learn to exploit or avoid. What emerges is not chaos but a new order, where perception itself becomes the ultimate competitive advantage. Picture colossal filter-feeding colonies, descendants of salps and pteropods, drifting through nutrient-rich layers, their bodies spanning tens of meters and housing billions of individuals linked by electrochemical networks. Each colony functions as a single sensing organism, sampling chemical composition across cubic kilometers of water, adjusting buoyancy and filtration rates based on multi-sensory predictions of bacterial blooms. They spawn in perfect synchrony with distant upwellings, their acoustic signals coordinating with electrical pulses to summon symbiotic cleaners and warning off predators. Around these living islands cluster smaller specialists, parasites that mimic colony signals to infiltrate, symbionts that enhance filtration efficiency, scavengers that process waste into usable detritus. The colonies themselves evolve defenses beyond physical barriers, emitting complex sensory disruptors that overload approaching predators with conflicting data streams. A synesthetic hunter drawn to the chemical promise of easy prey finds its perceptions scrambled, electrical fields inverted, acoustic maps distorted, chemical trails leading to nothingness. These vast organisms demonstrate that in the dark ocean, immensity serves perception as much as predation. On a planetary scale, the adapted ocean reveals patterns invisible during the sunlit era. Massive migrations guided by geomagnetic sensing follow iron-rich filaments snaking across ocean basins, herds of electroreceptive grazers trailing bacterial plumes that trace deep mantle convection. Chemical communication evolves to basin-wide scales, pheromonal gradients persisting for months, coordinating spawning across thousands of kilometers, synchronizing predator avoidance behaviors in species that never meet. Acoustic choruses, once confined to breeding seasons, become constant features of the soundscape, ecosystem-wide symphonies that convey information about food availability, predator density, environmental shifts. These aren't random noises but structured compositions, frequencies and rhythms encoding data that ripple through populations like living databases. Organisms tap into these choruses not just for local cues but for long-term trends, adjusting life histories based on acoustic histories spanning generations. The ocean breathes as one organism, its pulse detectable from space if satellites still watched. Within this grand symphony, horror lingers not in individual monsters, but in the ecosystem's relentless efficiency. Parasitic networks span species boundaries, chemosensory hijackers that reprogram host metabolism to favor bacterial farming, acoustic viruses that spread through sound-mediated behavioral changes. Colonial predators fuse into kilometer-scale hunting formations, their sensory fusion creating group minds capable of modeling prey evolution several generations ahead. Prey counter with distributed survival strategies, individuals sacrificing detectability to shield the group, chemical altruism that poisons predators while nourishing kin. Death feeds life with machine precision, detritus chains so efficient that 99% of biomass recycles within hours. The dark ocean wastes nothing, which means escape becomes mathematically impossible. Every organism contributes to the signals that will eventually lead to its consumption. Standing in this fully adapted world, the philosophical weight settles heavily. These creatures haven't merely survived the loss of light. They've transcended it, evolving perceptual ecologies richer than anything sunlight ever permitted. Vision was always a narrow window, filtering reality through photons. They've shattered that window, perceiving through chemistry, vibration, electricity, pressure and dimensions we cannot imagine. The mild horror isn't their strangeness but our sudden smallness, realizing that what we called the ocean's mysteries were mere shadows of deeper truths. Sight blinded us to the real ocean, the one humming with information across every scale and spectrum. In permanent darkness, life hasn't diminished. It's exploded into forms that make deep-sea vents look mundane. One final image lingers. A relic human submersible, its artificial lights carving tunnels through blackness, sonar pinging uselessly into the multisensory storm. Surrounding it, invisible to its crude instruments, drift the true ocean citizens, reading the sub's electrical hum, chemical exhaust, acoustic emissions pressure wake with casual precision. They sense the fragile lives inside perfectly, their collective awareness spanning the vessel's entire history from launch to this moment. We drift through their world as ghosts, our lights irrelevant, our machines blind. In this night without end, we are the ones who cannot see, adrift in an ocean that perceives us more completely than we could ever perceive it.